All right. Well, welcome back. We're going to carry on our way through this long, gruesome chapter. Our next one is as a model for electric quadrupole radiation, consider two oppositely oriented oscillating electric dipoles, separated by a distance d as shown in the diagram. Use the results of section 11.1.2 for the potentials of each dipole, but note that they are not located at the origin. Keeping only the terms of the first order in D, find the scalar and vector potentials, find the electric and magnetic fields, find the Poynting vector and the power radiated, and sketch the intensity profile as a function of theta. All right, well, let's see what we're looking at. So they mentioned a diagram, and indeed we have one. If we have a oscillating electric dipole on one end and another oscillating electric dipole on the other end, oriented the other way, now it looks like a quadrupole. Okay, so we have plus P naught cosine omega t and minus P naught cosine omega t. Here they're separated by a distance d. Again, we're trying to be symmetric about the origin, and we're going to some point in space P. So you see plus P naught has the plus script r, minus P naught has the minus script r. And then we form some angle theta. Okay. This is a cool diagram to get a head start, but it's not exactly what we're going to want as far as doodling up on and making something useful for the formulations we need. So let's redraw it and see that we have the, instead of having some main distance d, we have a d over 2 to split the difference from each dipole to the origin. And, you may recall that we've done kind of these multipole expansions for both the electric dipole and a magnetic dipole in other chapters, namely 3 and 5, or maybe 6, one of the two. But we've seen this set up before. So for the plus dipole, we have the plus r and theta plus. For the minus dipole, we have the theta minus and theta, and then r minus. So familiar setup, but the two diagrams are given as such. One is the model, one is what we're going to work off of. All right, so for part A, we saw that in section 11.1.2 that the potential was V equal negative P naught omega over 4 pi epsilon c times cosine theta r sine of omega evaluated at the retarded time t minus r over c. Okay, so using superposition, our goal now is to add the v at the plus and the v at the minus. Okay, so with that, if we just set up the v plus or minus, again, pretty typical in multipole expansions to kind of work this way. Then we get a minus plus on overall sign, and we have theta of plus or minus, r of plus or minus, and then again, sine omega at t minus r plus or minus with c. Okay, so we were told we want to keep everything within the first order to d, and that's fine, but we have to set up what r is, and we have to set up what theta plus or minus is. All right, let's start. So we use what looks like just the typical, law of cosines structure here. And what we see is that we get the an r squared, d squared, plus the crossover terms. The problem with this is that, again, we only want what's in the first order, right? So if that's the case, then the d over 2 squared doesn't give us that first order that we're actually looking for. So we just approximate it down. And that's where we get 1 plus d over r cosine theta after we factor an r out. Okay. Now from here we can just use the binomial expansion, or binomial approximation, which we've seen 100 times already in this book. I might even make a chart for it so we can see where it comes from. It's used so frequently. But it's a great way to get rid of the square root, and we just have to be careful with that minus plus and keep its orientation right. Because then if we're looking for 1 over r, we have to flip the r on its head and then change the sign inside. Okay, so that's what our plus or minus r's are. Now, if we want the cosine plus or minus, we have to be a little more careful. So here, if we're trying to set up an equivalent statement for, opposite side and then the hypotenuse, typical sine structures here, this is what we're actually left with. We have r cosine of the main angle from the origin minus plus d over 2 and then r plus or minus. So once we have that set up, now we can just chug everything through with r and divide it by r plus or minus. When we do that, we see, or times 1 over r plus or minus, you see we have an r that cancels, and then we just have to FOIL out or expand. But again, we were told we want first order and d. So we only do that up to the first order. Hence why the second term doesn't, the second expansion of minus plus and plus minus d over 2r is neglected. We do not have a d squared, only first order. After that, we see that we have a d over 2r. Again, we factored it out from the 1 and the cosine squared. And now we're able to put in a sine squared based on the Pythagorean relation. With all that setup work done, now we can just evaluate everything that we need. If we're going to start with the sine and evaluate that with the plus or minus r, multiply that cn, or the 1 over c, and simplify down. We see we get some cancellations here. We like that. And then we're going to allow t naught to be t minus r over c, so we can again have the retarded time in there. But, fair enough. Once we distribute it, now we can, once we substitute that in, now we can distribute the omega and use the sum and difference identities to get everything broken down further. So we do that, and that's what you see in the second line on the second slide. And then we just approximate to the first order, again, small angle identities. So we're good there. We like those approximations. It'll make the calculations simpler too. So now we can go back and plug in and simplify the expression itself, the scalar potential expression. Again, keeping in mind that we want to move things through accordingly. And when we do that, we see that we have that lingering 1 over r from the cosine substitution. And then, take that out front, Again, the goal here was to deploy to the first order. So now that we have something for the expression of the cosine plus or minus, and we have the expression for the 1 over r plus or minus, as well as the now expanded version of that sine omega, thanks to the sum and difference and small angle, we can distribute all of these, and again, we have to keep it to the first order. So our first distribution is the parentheses, which we see. We'll leave the bracket alone. After the parentheses, then we'll distribute it to the bracket terms. And again, we are neglecting any higher order terms in d. So if your expansion leads you to a d squared, we drop it. We don't want it in this approximation scheme. Okay, so finally then, we said that the scalar potential total was v plus and then add it with v minus. So now we have to take them two and add them together, and this is what we see in the next bracket. All right, so, nothing too crazy there. We just got to be very careful on the simplifying. And, when we factor out the d over c, omega d over c, then we have to kind of force the omega c in there on the middle term. And that's what we color-coded in blue. So with that, we're good to go. But let's note that our underlying assumption for the radiation zone was r is much less than omega over c. So the second term is negligible. And that was kind of the point. Now we can show that with omega, or that with r being so much bigger, it being in a fraction like that allows it to kind of whimper out. So we don't care about that second term. And, after that, then we plug in the actual potential here, the total, for when we're dealing with the radiation zone. And then instead of having omega t naught, we put the t naught back in there. So overall, I think we're doing pretty good. We have everything in terms of the original quantities. And in a similar gust, we can simply just push through the vector potential. So I'm not going to spend too much time with that, seeing as how we did everything pretty meticulously with the scalar potential. But that's what we boil down to. I tried color-coding it again to make it easy. But then when we try to add up the plus and minus to find the total, Again, we have to worry about that radiation condition of R much greater than omega over C. And we see that, factoring out leads to a certain particular way that gets rid of that, that gets rid of things after expansion. And you see here that we get the total field after we factor out a cosine. And then we have that C over omega R on that sine omega T at the very bottom, plus cosine omega T, again, in the radiation zone, that the R much greater than omega over C will drop that sine omega T naught term out. And that's what we see in the next slide. All right, so B, to simplify the notation, let's let alpha equal negative mu naught P naught omega squared D over 4 pi. Okay, now we can see these two things pretty clearly, or at least a little more tidy. Again, for the sake of the radiation zone, this is where we're at. Now that the hard part's done, let's go ahead and try to find the fields. We know we're going to need a gradient and a time derivative and then a curl. So the gradient of the scalar potential is given as such. Be very careful with your derivatives. You're going to have to use the chain rule on the r hat direction. And then, again, be careful with that chain rule with the sine and cosines in that numerator. Carry it down, cancel accordingly, tidy it up, and then you see we're only left with a radiation field component. Again, radiation field, we need something like 1 over r. We can't have 1 over r squared terms, hence the highlights in red. So we're only left with one component in the r hat direction, and yeah, that tidies up nice. Our next concentration here is taking a time derivative of the vector potential, and the only thing that has any time dependency is that cosine omega T naught. With that, we just get a factor of omega T out front, omega, and then we have a minus sign from the change in cosine to sine, but otherwise we're good to go with that. So then putting these results together in the next page, we see that we have E is equal to the negative gradient minus time derivative of A, and we see we get some cancellations of the R components. We like that. So we're left with E at the radiation field only. E is equal to the negative alpha omega over C R, and then sine theta cosine theta sine omega T naught in the theta hat direction, coolio. B we know was the curl of A, so we only need the representation of the representative derivative and components, namely theta, A theta, and AR. Considering that the Z hat can be written as R and theta components in the spherical sense. So yeah, apply the derivatives again very carefully. Again, we're going to get rid of, after we simplify down, we're going to get rid of anything that goes like 1 over r squared, which is what we see in red because that is not a radiation field. So we're left with the negative alpha omega over C squared r, sine theta cosine theta sine omega T naught in the phi hat direction. Okay, so finally then, we notice that, and for part C, that B is equal to 1 over C r cross E, and that r dot E goes to 0. Notice that it goes to 0 because we don't have any component in the r hat direction. So take that cross product, substitute in the definition for B, and we see that we can have a triple product there that we use backcap for. Easy enough, run it through, let it simplify, and then you see we get an expression for the Poynting vector, and we'll just be careful of the fact that the only time component there is that sine term in purple. So if we're looking for the intensity, we have to do the time average on it, and that's why we see the purple goes to the 1/2 because the time average of sine squared is 1/2. And then everything else is constant, so let it run through. There's our intensity. The power, we're going to have to set up the integral as you see. We get the normal 0 to 2 pi, 0 to pi of that intensity. And let it run its course. The r's cancel again. We get a 2 pi factor from the d phi. We get a sine squared or a sine cubed and a cosine squared in this case. So we're able to get a 4 over 15 for that. We like that. Then we just substitute in alpha and simplify and whittle away. We see that the power is mu naught over 60 pi c cubed, P naught d squared omega to the sixth. Okay, that omega to the sixth is kind of weird because we notice that it goes like omega to the sixth, whereas the dipole itself just goes like omega to the fourth. Interesting observation to note.